Multivariate methods chain complexity. In table 5.1, we see how the number of parameters of the covariance matrix may be reduced the trading of the comfort of a simple model with generality. Table 5.1 is reducing variance through simplifying assumptions. So if this assumption is a shared hyperspheric, and the covariance should be Si equals to S, which is equals to S squared times the identity matrix, and the number of parameters should be 1. If the assumption is shared and the axis aligned, and the covariance matrix will be Si equals to S with Sij equals to 0, and the number of parameters should be D. If the assumption is shared hyperellipsoidal, then the covariance matrix should be Si equals to S, and the number of parameters should be D times D plus 1 divided by 2. If the assumption is different hyperellipsoidal, then the covariance matrix should be Si, and the number of parameters should be K times D plus 1, then divided by 2. This is another example of a bias variance dilemma. When we make simplifying assumptions about the covariance matrices and decrease the number of parameters to be estimated, we risk introducing bias. See figure 5.7. On the other hand, if no such assumption is made and the matrices are arbitrary, the quadratic discriminant may have large variance and on small datasets. The ideal case depends on the complexity of the problem represented by the data at hand and the amount of data we have. When we have a small data set, even if the covariance matrices are different, it may be better to assume a shared covariance matrix. A single covariance matrix has fewer parameters and it can be estimated using more data, that is, instances of all classes. This corresponds to using linear discriminants, which is very frequently used in classification, and which we discuss in more detail in Chapter 10. Note that when we use Euclidean distance to measure similarity, we are assuming that all variables have the same variance and that they are independent. In many cases, this does not hold. For example, age and yearly income are in different units and are dependent in many contexts. In such a case, the inputs may be separately z-normalized in a preprocessing stage to have a zero mean and unit variance, and then Euclidean distance can be used. On the other hand, sometimes, even if the variables are dependent, it may be better to assume that they are independent and to use the naive Bayes classifier if we do not have enough data to calculate the dependency accurately. Friedman, 1989, proposed a method that combines all these as special cases, named regularized discriminant analysis, RDA. We remember that regularization corresponds to approaches where one starts with high variance and constrains toward lower variance at the risk of increasing bias. In the case of parametric classification with Gaussian densities, the covariance matrices can be written as a weighted average of the three special cases. That is, Si prime equals to alpha times sigma square times identity matrix plus beta times S plus 1 minus alpha minus beta times Si. When alpha and beta they are equals to 0, this leads to a quadratic classifier. When alpha is equals to 0 and the beta is equals to 1, the covariance matrices are shared and we get linear classifiers. When alpha is equals to 1 and the beta equals to 0, the covariance matrices are diagonal with sigma square on the diagonals, and we get the nearest mean classifier. In between these extremes, we get a whole variety of classifiers where alpha beta are optimized by cross-validation. Another approach to regularization when the dataset is small is one that uses a Bayesian approach by defining priors on μi and si, or that uses a cross-validation to choose the best of the 4 cases given in Table 5.1.